And today, from this class and to the next class, we'll cover the chapter 4, which is of the subsurface environment. So this will tell you about, we're going to discuss what's the pore water or the subsurface water composed of, and what's the temperature, how the temperature changes, and what influence factors are there affecting to the surface temperature, and the pressure, subsurface pressure. I guess the pressure will increase with that because of the water pressure, and we'll talk about the effect of the pressure and temperature on the fluid characteristic, because when you have a pressure and changing the temperature, that will change the viscosity and also the phase of hydrocarbons. So today we'll talk about the first two topics, the subsurface waters and the subsurface temperatures. Okay, there are two types of water in the subsurface. So I think if you are dealing with the very shallow subsurface environment, like the soil maybe up to 100 meter depth, the free water also that applies to the shallow subsurface environment. So you can either have the free water that can move very freely. So if you have a pressure difference, the water will move from one side to the other side, right? And there's a interstitial water that's absorbed on the minerals, so that it's like the water observed on the clay minerals. Like if you remember the double layer theory, then because of the negative charges, it attracts the water molecule and it makes the double diffuse layer. Right? So then this kind of interstitial water is very difficult to remove. For example, so imagine that you have a full of water, and imagine that you have a soil full of water, and you blow it with air, then you have some water remain at meniscus, right? So that there will be a limitation removing the water by blowing the water, by flowing the air, right? And that's called the residual water saturation. Sometimes SR. And this residual water saturation also is affected by this interstitial water. Right? If you have more clay, then the residual water saturation will be high. And if you have less clay, then your residual water saturation will be less. Huh? So you can think of either maybe you can think of the unsaturated soil. Okay, so the subsurface water are analyzed for several specific reasons. You can measure the electrical resistivity so that you can use that information for the SP logging interpretation or the resistivity logging interpretation. So this electrical resistivity of the formation water can be used, and that's very important to estimate the water saturation in the hydrocarbon saturation. And salinity often increases with proximity to hydrocarbon reservoir. So this is a good indication that you may have some hydrocarbons. And subsurface water contains traces of dissolved hydrocarbon gases. So you take the pore water sample and you analyze it for the gas component or the hydrocarbon component using what? Gas chromatography for ion chromatography or the HPLC, right? Liquid chromatography. So from that chemical analysis, you can also get some evidence, you can find the evidence of the presence of hydrocarbon. There are 4 types of subsurface water. First is the meteoric water. So it's just the tap water coming from rain. So rain gets permeated to the soil, and it may go deep, and it's often acidic, and salinity will be very low, right? So it will have a very low salinity, and there will be oxidizing. And the second category is the Kone water. And so Kone water is the water which have been buried in a closed hydraulic system and have not formed part of the hydraulic cycle for a long time. So this is the, so if you think about forming the sedimentary rock, you will have a sediment flowing from the river, and it will settle down, and it's going to be thicker and thicker, right? Because you have a keep coming solid. Huh? And imagine that the pore water has not been circulated, or it didn't move, and it was just there for a long time, and it gets very deep, and then it becomes a Kone water. So it's very different. It is different from the sea water. And so, yeah, that's the Kone water. And the juvenile water are from the magmatic origin. So it's very deep region, and it is formed from the heat and the pressure by the magma. And of course, you have the also mixed origin. So some region you have Kone water and the surface water and meteoric water mixed up, and some region that you have Kone water and the juvenile water mixed up. Then there are different characteristics. So you can think of the pH and the salinity, or pH and the reduction potential. So if you look at this chart, the base, the alkaline character is in the right side, and the acidic is the left side, right? And as you go up, it has oxidizing potential here, and as you go down, you have a reduction potential. So the rainwater is in here. So it's quite acidic and oxidizing. It has oxidizing potential. And the seawater is here, meteoric water is here. So it's about a little bit alkaline. And Kone water is here. There's a redox. It has a reducing potential, and it's a little bit basic. And this reduction potential and the pH or pore fluid controls the precipitation and dissolution of the clay and other mineral in the rock. Okay, so then the salinity of pore water or the Kone water is very important, and it's been people use the TDS, the total dissolved solid, TDS, and its unit is in ppm. And people also use the milligram per liter for density. So let's just calculate. For example, what would be the how much would that be for in ppm if you have a 3.5% seawater? 계산할 수 있겠니? Can you calculate this? So ppm is the parts per million, right? So for example, 1 ppm will be 10 to 1 over 10 to the 6. Right? So it could be milligram per milligram or gram per gram, doesn't matter. Right? Let's say the milligram per milligram. Then how much would that be here for the in ppm? 3.5% seawater. I'll give you maybe 2 minutes. So what do you have? Anyone have the number? 계산한 사람? 응? 얼마 나오니? 중복. 35,000? 35,000? So I have four. So I have 35,000 ppm. So what I did is that 3.5% means that you have a 3.5 gram per 100 gram, right? And to make it, to convert it to the ppm, I put the 10 to the 6 gram at the bottom. So then to make it equal, then 10 to the 4 gram, eliminate that. So and then this becomes there 3.5 ppm, right? So then you have 10 to the 4 left over, so that if you combine that 35,000 ppm. Right? And how about if you convert it to milligram per liter, how much is it? Let's assume that the density of water is 1,000 kilogram per cubic meter or 1 kilogram per liter. 얼마나? 35 million? 아닌가? gram per liter, 35 gram per liter. So or you have the same number, right? 35,000 milligram per liter. By the way, how much is the molar concentration of seawater generally? Let's say that we have a 3.5% sodium chloride. And that would be in molar concentration, how much would that be? Just give me a rough number. Christine. No idea. What's the molar weight of sodium chloride? Sodium is 23 approximately, right? And the chloride is about 35.5, something like that, right? 35.5. Then molar concentration here is right. This number may be a little bit different from the actual number, but let's assume that. Then here you have 35 gram per 1,000 gram. So 35 per divided by 58.5, then it gives you the mole, right? And 1,000 gram is about 1 liter. So then this will give you the molar concentration, approximate number. How much is it? If you divide the 35 with 58.5, what do you get? Calculating. Anyone having calculator? 35 나누기 58.5. 그냥. 0.6? Okay, that's about the. So this is the approximate molar concentration of the seawater. Just to, just for your information. It's convenient to memorize this number. Okay, so the 0 ppm for fresh water up to 600,000 ppm for brine, and so this is much saline, much more saline than the seawater. And in Kone water, TDS seldom exceeds 350,000 ppm, so 10 times of the seawater. In sand, salinity of the Kone water generally increases with depth, ranging from 80 milligram per liter per meter and 300 milligram per liter per meter. So this is the concentration gradient. Right? So it tells you that, like for example, if it's 100, then 100 milligram per liter concentration will increase every 1 meter deep. Right? If you go deeper, as you go deeper, every 1 meter, the concentration will increase by 100 milligram per liter. Right? So this is divided by the meter here, the gradient. I just got the number from textbook. textbook에 어떤 자기가 본 이 저자가 the author, so this is the record that the textbook author have seen so far. So this is the field measurement, actually. So there could be a more saline brine. Okay. So any question so far? Okay. Good. So when we look at the concentration, actually the salinity increases with depth. So it's gonna increase as you go deeper. But the local reversal of this general trend can be found, and that's attributed to the two causes. First is the meteoric water may sometimes be trapped beneath an unconformity, and is thus preserved as a paleo aquifer. So, for example, sub-Cretaceous unconformity of the Israel, 60,000 ppm above the unconformity, but 20,000 ppm beneath the unconformity, and gradually increasing again with the depth to more than 40,000 ppm. So sometimes you have the more saline water at the top, and you have very diluted water at the bottom, but that's because of the trapped water. The meteoric water the rainwater has been trapped by the structure, geologic structure. And also, when you have the decreasing salinity with depth, is also found in overpressure zone. Overpressure zone means that the pressure has been preserved for for a geologic time, could be 1,000 years or 10,000 years or 100,000 years, right? So that overpressure was kind of isolated from the neighboring region by this geologic rock with a very, very low permeability. So there's a high chance meeting this local reversal of concentration because they don't communicate with the other cooling water next to it. As water moves up through compacting sediments, the shale prevents the salt ions from escaping from the sand. So in shale, the increase in salinity with depth is less marked. So you don't see general trends. The salinity of the sand is often about 3 times that of the shale. So when you have a shale and sand interbedded together, shale will have a lower salinity and the sand will have high salinity because the shale will act as a blanket. It blocks the ion movement, so they will trap the ions inside the sand formation. So unconformity. But in Korean 부정합, if you learn it from the high school or science class, have you heard of it? Unconformity in German? So if you learn the geophysics or the earth science in the high school class, the 부정합 있죠? 정합, 부정합 있죠? Unconformity is that when you have an irregular surface of the strata, the formation strata, so that can happen by numerous reasons. And the 3 types of unconformity is unconformity, angular unconformity, and non-conformity. And you can see that how it forms. So you have a deposition. This is a standard deposition. So you have a very parallel and flat layers. And when there's a tectonic movement, you have folding and uplifting, and there could be an erosion afterwards, so they get flattened. Then there will be a sequential, subsequential deposition, then you have unconformity. Right? 기억나죠? 지구학 시간에 배웠던 게 조금씩. So this shows you an example of the unconformity. So you have this conformity and angular unconformities. Angular unconformity is that you have a very steep angle of the structures, of the formation structures. And this picture also shows the unconformity here, right? And there are more. Here also unconformity. And so back to the pore water concentration. So you can see that this pore water concentration increases with depth, and people have categorized the region, the subsurface, into 4 categories. So zone 1 is the shallowest one, and zone 4 is the deepest one, and zone 1 is the surface to the depth of 1 kilometer, and salinity is fairly uniform. So you have a circulation of the meteoric water, and in zone 2, that depth is about 1 kilometer to 3 kilometer, and so salinity increases with the depth, and it's mostly the cone water. And you have the zone 3 that's deeper than 3 kilometer, and the salinity is uniform with depth, and the chemically reducing environment. And also at the depth, at this zone 3 depth, you have a generation of the hydrocarbon. It could be a chemical or a microbial. And zone 4 is near the metamorphic area. So you have very high pressure, maybe like area close to the volcanic area. Right? And then you have very high pressure and the temperature. Also the very geochemical reaction is going on, so that you have recrystallization of the clays to mica will happen. So if you have an overpressure zone, then you have reverse tendency of increasing salinity with depth, right? So the salinity will go this direction, and proximity to evaporite is evaporite is actually the salt dome. So it's a halite or made of sodium chloride. So as you go near the salt dome, the salinity will increase. And the lateral salinity variation. So we've been talking about the vertical salinity variation and what happens with if you move horizontally at the same depth. So salinity tends to increase from the margins of basin towards its center. So that means that where is the margin? So margin is here. It's a continental margin. And this is the center that you have a seafloor spreading. So as you go this direction, you have a salinity increase. So basin margins are more susceptible to circulating meteoric water. So you have a lot of water coming from the land. Then in the basin center, where the flow is negligible and coming from below. And regional isohaline map can be a useful exploration tool indicating areas of anomaly of high salinity. And these areas are presumably stagnant region unaffected by the meteoric water, where the oil and gas accumulation may have been preserved. So you can map the also salinity in the ocean. Okay. Just to give you an idea. So here you have an onshore, right? The continental, and you have margin. So this is the continental margin area. And always because of the tectonic circulation, you've seen that the 해령 해구 배웠죠? So you have a ridge, oceanic ridge. There's a new plate is generating. So here you don't have the surface water coming in right here because it's too deep and it's just so far away from the continental region. So there's only water coming from the bottom, so that you have very high salinity in this region. But as you go here towards the continental margin, you have a salinity decrease because now the meteoric water comes in. So just to, I guess it's if you convert it, translate it into Korean, it might be more familiar to you, but just giving you a chance to be familiar with this kind of terminology. Oceanic ridge, 이게 해령이고, and oceanic crust, you have a crust and the continental slope and continental shelf. 질문, question? So, see another example of the geologic terminology. Here, so you can think of Japan here. So Japan is very active area of volcanic activity, right? So you have volcano here with that makes some island, right? And then the back arc. So the front of this magmatic arc is the fore-arc, and the back side is called the back arc basin. So here, if you think of this is the Korea, and this is Japan, and here is the Ulrum Basin, back arc basin, and as you go here is the Pacific Ocean. You have a subduction zone here. Okay? And so another example is that you have a Gulf of Mexico, and here in the Najas Arc. Okay, so this is the same configuration. You have Japan here, magmatic arc and fore-arc, and as you go toward this direction, it's the Pacific Ocean. Here you have a Korean Peninsula, and this is the back arc basin, which is Ulrum Basin. It's fun, right? Okay. Then what will be the chemical composition of the subsurface water? Subsurface water contains inorganic salts and organic compounds, including hydrocarbons. If you look at the major components in seawater and some pore water sampled from different regions here. So here is about, it's about 10 kilometers, 1 kilometer deep. And this is seawater. So you have a chloride in seawater and sulfate and carbonate and bicarbonate and sodium, potassium. That's the major cation here. And as a secondary component, you have a calcium and magnesium. And total ppm is 35,000 ppm. And here, if you look at the number, the salinity in terms of the TDS is very much higher than this seawater. It's about 100,000 or 200,000 ppm. And major component cations are sodium and potassium. And you have some calcium, magnesium. And for the anion, the major component is the chloride. And in some location, you also have the sulfate and the carbonate. So the metallic water have higher concentration of the bicarbonate and sulfate and lower amount of the calcium and magnesium. And cornell water differ from seawater, and cornell water contains the lower percentage of the sulfate, magnesium, open calcium, and a higher percentage of sodium, potassium, and the chloride than does the seawater. The general characteristic and differences between carbonate and this metallic water. Yeah, I think we can read this. So cornell water also contains traces of dissolved hydrocarbon, methane, ethane, propane, and the dissolved gas is increased with depth and from basin margin to center and near oil field. The regional maps of dissolved gas content can be used as key to locating new oil and gas fields. Okay. So far we talked about the subsurface water, the salinity changes, and the chemical composition. 질문 혹시 여기까지? straightforward인가 너무? Okay, we'll talk about the subsurface temperature. Temperature is geothermal temperature are is important because it is related to the generation of the hydrocarbon. So you have to have some warm and hot temperatures to produce the hydrocarbon. So either the bottom hole, so when you drill the hole, they measure the bottom hole temperature, BHT, so that, and they can draw a line with depth, the temperature traces with depth, and it gives you a linear line like this. And so then gradient is called the geothermal gradient. Right? This is the one. Well, here it says here. Sorry, the geothermal gradient. Right? So geothermal gradient, the unit will be what? The degree or temperature, like Celsius or the Kelvin per meter or Kelvin per kilometer. So these value ranges from 1.8 to 5.5 degrees Celsius per 100 meter. So let's say, let's look at this global average. It's a 2.6 degree per 100 meter. So if we say that 10 degrees Celsius at the surface, then 1 kilometer deep, how much is the temperature? If you look at the average geothermal gradient. 얼마나 되죠? 10 plus 2.6 times 10, then becomes 36. And 2 kilometer, it's about 50, right? And 3 kilometers are 75, and it's going to keep increasing, right? And in the onshore, generally this geothermal gradient is higher than the offshore. Actually, there is from region to region. So basic principle, the geothermal gradient may not be constant with depth, and this discrepancy is generally caused by variations in thermal conductivity of penetrated strata. So you have a constant heat flow from the core of the Earth. So core, you have a heat flux, and let's say that I can show you the later, but if you have a heat flux coming, and if you have a very high conductive material, the thermal conductivity, the material with the high thermal conductivity, it will pass through the heat very well, right? But if you have a low conductivity material, then it's gonna trap. It will insulate the heat, right? So that the temperature of that formation will be higher than the other formation. So the thermal conductivity of the formation will determine the geothermal gradient. It will affect it. I can show you the example. And let's look at the numbers for the thermal conductivity. The water has 0.5 to 0.6 watts per meter Kelvin. And thermal conductivity increases with decreasing porosity and increasing depth. So, and also the mineral type is very important. It affects the thermal conductivity of the bulk rock. So halite is made of sodium chloride. It has high conductivity. And sandstone 2.6 to 4, the shale 1.5, and coal 0.3. So you can see the range of the thermal conductivity. So it is about 1 to maybe 5, right, at most. And the bulk thermal conductivity is affected by the water saturation, and the conductivity of water, and the rock mineral thermal conductivity and porosity. So this gives you an idea how each rock formation affects the geothermal gradient. So here you have, so let's look at the number. This is the rock thermal conductivity and the porosity. And this is the bulk PR. It's bulk thermal conductivity. So when you look at the number, this region has very high thermal conductivity, right? High K. And here you have a low K. So, and in the low K, low thermal conductivity material, you have very high temperature gradient, or low temperature gradient. And here you have no, it's the other way. It's the other way. This is the, sorry, so this is the temperature. So thermal conductivity increases and the gradient decreases with depth and declining porosity. And local vertical variation are due to lithology, especially the high thermal conductivity of the evaporite. So here, this region is made of the evaporite and salt. And the other example is in the next slide. Here, which one is the biggest one? Okay. Geothermal gradient. Let's look at the geothermal gradient. here the 4 is the largest one, and the 3 is the smallest one. Okay. So smallest means that you have a less increase for the same depth increment. Then K3 will have the largest thermal conductivity, and K4 will have the lowest thermal conductivity. Can you understand it? So the low conductivity material will insulate the heat, will trap the heat, so that it will increase the temperature faster. It will have the higher temperature. The high thermal conductivity material will pass it through, the heat will just pass it through well, so that the temperature increase will be less than the one with the lower one. So if you draw the line of constant temperature, it's called the isotherm. Then, for example, here, okay, I think it's in 10 degree Celsius interval, 40, 30, 20, and 50, 60, 70, right? So you have in the high geothermal gradient region, you have a closely spaced isotherm, and the low geothermal gradient region, you have a widely spaced isothermal contour. So vertical spacing of the isotherm decreases with the decreasing conductivity and increasing geothermal gradient. It is very obvious. The isotherms are seldom laterally horizontal or very far because of the following three factors. So non-planar geometry of the sediment and movement of the fluid and regional variation in heat flow. I can show you one example. So if it's just a planar deposition, then you have an isotherm flat and parallel horizontally. But in this case, you have a salt dome, and which is intruding upward, so that this is high K, and this is the low K, low thermal conductivity and low thermal conductivity. So here you have less, when you look at the isotherm, it's a widely spacing. And here you have a more closely spacing geothermal. And salt dome has because salt has a far higher conductivity than most sediments. So here the isotherm dome up over the salt diaper, and it depresses underneath it because of the high thermal conductivity of evaporite of the salt dome. So when you compare the number above it, it's about 1.74, and below it's 2.8, but in the salt dome it's about 4.2, so very high thermal conductivity. Okay. So local thermal variation. Contrast to salt mud diapers of highly porous overpressure clay have anomalous low thermal conductivity. So another extreme, so the one extreme with the high thermal conductivity is salt dome, and the other one with the low thermal conductivity is mud diaper. And the extensive overpressure clay formation acts as an insulating blanket, trapping thermal energy and aiding source rock maturation. And igneous intrusions may cause positive heat flow anomalies long after the magma was in place. The resulting thermal chimney may result in the development of a convection cell that draws the condensate water into the flanks of the intrusion and expels it from the crest. So if you have a magma intrusion right there, the water comes in and here, like this. Comes into the flank, and it expels it from the crest. So this mechanism may be responsible for the emplacement of the petroleum impacted reservoirs in the granite. So then heat flow of the Earth's crust. The heat flow is the, I showed you the example before, geothermal gradient times thermal conductivity. So let's calculate the unit. So geothermal is per meter, right? Or maybe Kelvin per meter. And the thermal conductivity unit is what? Watt per meter Kelvin. Right? So let's use the Kelvin, right? This one. Then the heat flow or the flux will be, let's calculate it. Kelvin per meter, that's the geothermal gradient, times watt per meter Kelvin. So then, what do you have? Kelvin, it's both will cancel out. You have watt per meter square. And if you convert it to joule, because the joule, 1 joule is the 1 watt second, so then joule per meter square and second is the same thing. So this is the unit for the heat flux. Right. So the energy passing through a unit area per second is the dimension for the heat flux, or the watt per unit area is the dimension for it. It's the same. So the average heat flow rate is 1.5 microcalorie per square centimeter second, and high heat flow occurs along the mid-ocean ridges and intercratonic rifts where magma is rising to the surface and the crust is thinning and separating, and low heat flow at the convergent place boundaries where relatively cold sediments have been subjected into the mantle. So in the middle of the ocean, if you have a ridge where the plate is coming out, generating, then you have a high heat flow, and the subduction zone, because the cold one is going down, so that you have a low heat flow, heat flux. Okay. The oil generation occurs between the temperature of 60 and 120 degrees Celsius. So that's the optimal temperature range that people have found so far. And increase in areas of the high heat flow, hence the high geothermal gradient, the optimal temperature will be reached at the shallow depths. This is obvious. And the oil generation begins at the greater depth in subductive trough than in the rift basin because of the different heat flux. So if you have a high heat flow, then you have a high geothermal gradient, and low heat flow, you have a low geothermal gradient. Move on. Okay. Okay, then let's have maybe 10 to 15 minutes talking about the thermal conductivity of soils and rock. Okay. So far, any question? 여기까지? 질문? Comment? So, how can we measure the thermal conductivity of soils and rock? Or any solid, or the liquid, water, gas. So thermal conductivity is one of the physical property, like a density, right? Or like maybe strength, or the permeability. It's one of the physical properties very important in the geotechnical engineering and the geology, right? So these days, people use the shallow geothermal energy or deep geothermal energy. There's also the many infrastructures related to the energy and the heat, so that the finding and investigation of the thermal conductivity is important here for the geotechnical engineers. So the people use the thermal proof method. So this method is the basic theory for the thermal proof method. And the governing equation, so assume that you have a line heater that infinitely long inserted in the medium, so that what we are trying to do is that we are trying to find the thermal conductivity of this medium, right, surrounding this line heater. And then when there's a heat flux coming out of the line heater, then the temperature change around this line heater can be expressed by this equation, the first one. So this is the radial heat flow. Describe the temperature changes in radial direction. So you have R, that's the radius from, maybe it could be the distance from the heat. And the theta is the angle. And if you solve this equation for this boundary condition, we have a infinite line heat source, and you have this closed form equation. The temperature at the distance r at the time t is function of q and the lambda and some geometric value I. And this I is actually the coefficient c minus ln x plus some other factors here. But you can ignore this, the third one and fourth one and the one after that, so that we can just have these two factors. Then final equation becomes this one. What does it tell you? So this tells you the temperature at a given time, maybe like 1 second later or 1 hour later, any time of interest, and any distance of interest, maybe 1 meter away from the heater or maybe 10 meters away from the heater. Right? Because it's a long infinite one, you don't want to, the temperature at here, at the same radius, it's going to be the same, right? So this is a function of Q, that's the heat flux, and the gamma, that's the thermal conductivity of the material, and the C is the just coefficient, R is the distance, alpha is the thermal diffusivity of the material, and T is the time. So then, if we can find the temperature change at time 1 and time 2, so between these two time intervals, then we can simplify the equation to this one, and from this equation, we can calculate the lambda. So lambda will be, if you manipulate this equation, Q over 4 pi times 1 over delta T over ln T2 over T1. So this is the final equation people use to calculate the thermal conductivity lambda for a given heat flux Q. And I can show you the results. So if you have a long heater, electrical heater, inserted into some solid, any porous media, the rock or the soil, then you apply the voltage to this electrical heater, and you have a temperature change like this. So then the first region, you have a temperature increase from the beginning of the application of the voltage of the electrical current. Then you have temperature increase like this, and at some point you have a linear portion, and then there will be some effect by the boundary. If there's no boundary, if you have an infinite medium, then you have the infinite linear portion. It's going to increase like this. But this one is just the boundary effect. So then, from this equation, please note that this is the logarithmic scale. And then delta T over ln T2 over T1 is what? This slope, right? Slope is T2 minus T1 over ln T2 minus ln small t1. And this will be T2 minus T1 over ln T2 over T1. So this equation is basically the same as this equation, 1 over slope times Q over 4 pi. And the Q, how can we calculate the heat flux? Heat flux is actually can be calculated from the electrical current and the voltage that you apply to the heater. So this is V. Here the V is the voltage, the potential that you apply to the heater, and the I is the current, electrical current going through the heater. So from that you can calculate the heat flux. So this is the general setup, that you have a thin probe which have a heating wire, and also it has the temperature sensor inside. So for example, this is the one. I think you may be familiar with that. So it's this, along this stainless steel tube, inside it has an electrical heater, and at the center you have a temperature sensor. So it records the temperature changes, and when you apply the electrical current and the voltage to this line. Right? So you can put this probe to the soil and measures the temperature changes. So when you have a heat flux, so heat flux is given by the electrical electronics, right? It could be a power supply. And if you have a very high thermal conductivity material, like what? Like copper. Right? It's a metal, so it has a high thermal conductivity material, right? Then what will be the temperature trend? Temperature will increase fast or slowly? Fast? Why? Yes. High conductive means that it can flow the heat flux easily. So then, for a given heat flux, it will pass the heat. The energy will just flow. So the temperature increase will be actually low. Increasing rate will be low. So you can think of the opposite way. So if you just insulate it with the maybe cotton ball, right? It has very low conductivity, then heat will not escape. Right? It cannot escape. So the heat will be trapped inside, so that you have very high increase in temperature. Temperature will rise very fast. So that then we can analyze the slope. So slope means that the rate of the temperature increase, right? So if you have a high slope, very steep slope, then the thermal conductivity will be low, and low slope, a gentle slope, then the thermal conductivity will be high. So that's how it works. So then you apply the constant voltage to the heater, measure the voltage, and also you measure the electrical current to calculate the Q, and record the temperature change, delta T with time, and you know the Q, and you can calculate the slope, then you have everything to calculate the lambda. Then, so let's do the exercise. Yeah? So this is the example that I measured in the dry sand. So actually I use this dry sand, and here we have a temperature sensor. And then you guys can calculate the lambda from these values. Okay, I'll give you maybe 3 minutes to calculate the Q and the slope and the lambda. How much is the Q? So your voltage 8.03 and the current is 0.051 ampere. And heat resistance is, so actually this is from V time R, and here V is IR from the Ohm's law. Sorry, it's wrong. I square R, should be I square R. Do you have this number? I square R, does it give you the same number? I may be wrong. So 0.051 times square times 950. 얼마 나오니? 아니, 2.47 watts per meter. Do you get the same number? So this is the heat flux that you apply to the heater. And then you get the temperature change like this. And probably we can select the linear region here from here to here. So that's 20 seconds to 100 seconds. Then we can calculate the slope. At 20 seconds, the temperature was 7.242. And at 100 seconds, the temperature was 8.664. So from this, calculate the slope in logarithmic scale. So slope should be T2 minus T1 over ln T2 minus T1. 슬로프 구한 사람. 이거 얼마 나오니? So you get this value for the slope for this linear region from 20 seconds to 100 seconds. Then you can plug that number, this number to this equation. Right? You have a Q and 4 pi and 1 over slope. Right? Then you get this lambda. I think if you calculate correctly, then you get the thermal conductivity value as 0.247. 비슷하게 나오니? Okay, so that's how you calculate the thermal conductivity from the thermal proof method. So I'll show you the demo. 이 다음 뭐지? 아, 데이터구나. 잠깐 나와보십시오. We can show you the demo. So I brought the equipment that can measure the thermal conductivity. So this is the thermal proof, and we have dry soil and the saturated soil. Dry soil is, so if you compare this one, which one will have the higher thermal conductivity? 뭐가 더 열을 잘 발산할까? Saturated, 그지? Because air has low thermal conductivity, almost zero. The water has 0.5 watt per meter Kelvin. Right? So if you measure it, actually, this will give you about 0.2, 0.3. 근데 이거는 this will give you 2, more than 2. So I think let's do this one first. So I'll put this one like this, and then it has a power supply, and it records the data. Okay. So now I start to apply the 8 volt and the current is about 50 milliampere set here, and temperature is increasing like this. Now the temperature is 30. It's increasing. So you measure it over time. Generally, the measurement time takes 5 minutes, 5분 정도. 그러면 then you can plot it over log t and the delta t. Right? Delta t versus log t. 그거 가지고 then you can plot it and then you can find the linear region and then you get the same curve that we've seen in the previous slide. Okay, 가십시오. Okay. Then we'll close it very soon. So then it's gonna take about 5 minutes, so I'll show you the results later. So thermal conductivity versus effective stress. So it's from actually the one of my master students did a wonderful experiment, and she got the data, beautiful data, and this is the data. So when you have a dry sand at the medium dense or the dense and medium dense and the loose state, let's look at the loose state. Here you have 0.27, right? And it increases like this, and when you unload it, it becomes like this. So you have an increase in thermal conductivity with increasing vertical effective stress from here to here, and then you have unloading cycle like this. So as you increase the effective stress, what happens in the grain contact? They get larger area for the grain contact, right? So that they can conduct the heat more readily. And so that's why you see the increase in thermal conductivity. And what happens in the saturated soil? You can see the value. The value here is totally different. It's more than 2.8 watt per meter Kelvin. Here, 0.28, right? So the ranges are different because of the water. And also you can see some increase in thermal conductivity with the increasing effective stress. And this is the result with the porosity change. Porosity, so as you have denser packing, you have a more coordination number. So the one particle will touch more particle, neighboring particle, so that you have a more path to conduct the heat. So that thermal conductivity increases as the porosity decreases. Right? That's for the saturated sand together. And the last one is that thermal conductivity versus the water saturation. So keeping the porosity same, you are adding the water. And then as the water fills the void or the pore, the thermal conductivity increases following this line. So here the initial value is less than 0.5. And the final value when it's fully saturated is more than 3 for the quartz sand. So suggested readings are these two papers. I will send you the papers later. Okay?